Lecture 5, Part 1, Introduction to Probability. First, let's start off by looking at the procedure. In this chapter, we assume that population is known and calculate the chances of obtaining various samples from that population. This is the reverse of the logic of what we have done thus far. So in probability, we tend to use the population to infer the probable nature of a sample. The probability of an outcome is the long-run percentage of times that you expect the outcome to occur. The probability describes the relative possibility, chance, likelihood that an event will occur. A probability is a value between 0 and 1 inclusive, describing the relative possibility, chance, or likelihood an event will occur. Every probability is a percentage between 0 and 100, and in terms of decimals, a probability is a number between 1 and 0. A probability of 1 means that the outcome will occur with certainty, and a probability of 0 means that the outcome is impossible. Let's have a look at this example. Suppose you buy a lottery ticket and have to pick 5 numbers from 1 through 60, repetitions not allowed. Which of the following combinations is more likely? Combination A, which has numbers like 12, 48, 49, 17, 35, or combinations like B, which has numbers of 1, 2, 3, 4, and 5. So for the most part, right, we understand that, the probabilities of these two events is entirely exactly the same. The probability of the first ball being selected being 12 is 1 out of 60. The probability of the first ball being selected being a 1 is also 1 out of 60. The probability of the second ball being selected of 48 is 1 out of 59. And the probability of the second ball being selected as 2 is also 1 out of 59. Therefore, A and B have exactly the same probability of occurrence. Therefore, does it matter which of these types of lottery tickets you choose? Not really. However, what we understand about the lottery is we understand that we really typically don't see very much of this type of consecutive or sequential numbers, right? We do tend to see a more dispersed number set, which can lead us to some misconceptions about probability. Some misconceptions. First, believing that outcomes that appear to be more random have a higher chance of occurring than outcomes that don't, like the previous example. Thinking probability works well for predicting short-term behavior, and that is absolutely not correct, because probabilities are basically looking at all possible outcomes and selecting a certain specific outcome from the whole. Claiming you can be on a roll by law of averages, again, that is a common misconception. And also treating any situation with only 2 possible outcomes as 50-50. We know that many situations that have 2 possible outcomes do not have these types of odds, and they have very different odds in terms of outcomes. So range of possibilities. So for example, the probability the sun will disappear this year, the probability is 0. Actually, it's 2020, so you never know what's possible anymore. The chance of a head in a single coin toss, that's 50%. And the chance of rain in Florida this year at some point is 100% or equal to 1. Probabilities could be anywhere along the spectrum. Let's have a look at a few definitions. Here we're going to define the words experiments, outcomes, and events. An experiment is a process that leads to the occurrence of one and only one of several possible observations. An outcome is a particular result of an experiment. Event is a collection of one or more outcomes of an experiment. Let's think of a coin toss, right? In the coin toss itself, the experiment is going to be the act of tossing the coin and seeing the result of that coin. The outcome is what you read. Is it heads or is it tails, right? That's going to be the outcome. The event is an occurrence where if we flip the coin many, many times, recorded heads or tails and what the outcomes were, the collection would have become our event. A few more definitions. First, mutually exclusive events. Events are mutually exclusive if the occurrence of any one event means that none of the other events can occur at the same time. For example, if you toss a coin, If you see tails, you cannot also see heads simultaneously. So mutually exclusive events are events that are completely separate from each other. There's no overlap in terms of the mutually exclusive events. Next definition is collectively exhaustive. Events are collectively exhaustive if at least one event occurs when an experiment is conducted. So basically it's saying every time you toss a coin, you're going to see at least one of the events, which is you're going to see either heads or tails. If you toss a coin in, an earth setting and the coin comes back down, you're going to get an idea of whether it's heads or tails. It's impossible for you not to see an outcome. So the set of ideas is inclusive of all possible options. The sum of all collectively exhaustive and mutually exclusive events is equal to 100%. Independence. Events are independent if the occurrence of one event does not affect the occurrence of another. So for example, when we toss a coin and the first coin toss yields heads, does that change the probability of what the second coin toss will yield? Well, in fact, there's absolutely no impact of what you see in your first coin toss to what you see in your second. So if the probability of tails of the first coin toss is half, you toss the coin, you get tails, and that means the probability of the second coin toss being tails is still half, which means these events are independent. If events are not independent, then they have a conditional or dependent probability. This means there's an additional knowledge that can alter the pre-established probabilities. Probability of one event is dependent on the results of previous events. Here, one thing that I like to do is set up the order of the events taking place. Event 1 occurs, event 2 occurs, etc. Let's look at an example. Let's say we have a standard deck of cards. If we draw a card from a standard deck, let's start with our first experiment. What is the probability that our first card is a king of hearts? There's only one king of hearts out of 52 in the deck, therefore that probability is 1 in 52. If you take the card out, and let's try a second experiment. Second experiment, once we took out that king of hearts and put it in our pocket, what is the probability of the next card being a queen of hearts? Well, since you've removed one of the cards from the deck, and there's only one queen in the deck, the probability of the next card being a queen is 1 out of 52. So conditional probability means that there's an event that has occurred, right? In this case, selection of the king of hearts, that alters the outcome of all future events, namely the probability of selecting a queen of hearts. Let's look at an equation here. The first equation we're going to see in this chapter is for classical probability. This is also known as theoretical probability. The probability of an event is calculated as such: the number of favorable outcomes divided by the total number of possible outcomes. So the first thing we need to do is we need to figure out how many possible outcomes there are in any given experiment, and then figure out what we want to know the probability of. So for example, what is the probability that a coin toss will yield tails? In this case, our favorable outcome is tails, so that's going to be our numerator. How many total tails in any set of coin toss? There's, of course, one. So there's one favorable outcome. The total number of outcomes possible every time we toss a coin, we can see either heads or tails, therefore there's 2 possible outcomes. So in terms of our experiment, there is 1 out of 2 possible outcomes that the coin toss will yield heads. So the probability that our coin toss will yield heads is 1/2 or 50%. The complement rule. The complement rule is used to determine the probability of an event occurring by subtracting the probability of the event not occurring. So if we think of event A as the probability of event A, whatever event A may be, this green section where you see little tilde here and A, that basically means everything that is not A. So in certain cases, if we were looking to find the probability of A, we could take the whole, which is the collective exhaustive 1, minus the probability that A does not occur. This is our complement rule. Experiments and outcomes. So again, just to refresh our memory of our definitions, If we tossed a coin one single time, the outcome we'd have two possible outcomes, heads or tails. If we tossed a dice one single time, there's 6 possible outcomes, a 1, a 2, 3, 4, 5, or 6. If we do we toss 2 coins simultaneously, in that case we have 4 possible outcomes. Either we can see 2 heads, a head and a tail and a head, or a tail and a tail. So those are all 4 outcomes. This brings us to the law of large numbers. The law of large numbers states that the more times an experiment is repeated, the closer the probability of each outcome gets closer to the actual probability. So we can look and compare outcomes of 5 consecutive coin tosses, 50, 500, or 5,000. What we tend to find is that the more coin tosses you do, the more likely you are to have an equal distribution of heads and tails in all your outcomes. This is a coin toss repetition. So here you see the number of times the coin was tossed, and this is the proportion of heads to tails. Notice that initially when the coin has just been tossed about, say, 200 times, you're still seeing quite a bit of fluctuation around that 50% line here. But as we get to the 1,000 mark, we start to see the margin of error start to narrow between that 50%. And if we kept going and went to 5,000 coin tosses, we'd start to get closer and closer to basically staying at that 50% mark.
In the 16th century, an Italian mathematician named Cardano had a well-known gambling addiction. He wrote letters in which he bragged about his ability to beat his friends at dice games. His trick was to place his bets using his ideas from mathematics instead of hunches or luck. He came up with a method of calculating the exact probability of random events, such as, say, rolling snake eyes. It is based on a powerful property Cardano noticed. Every outcome, no matter how many dice you roll, is equally likely. This allowed him to calculate the probability by developing what's now called a probability space. First, he counts all possible outcomes, known as the sample space. For a single dice, these are the 6 possible faces. Then he defines the event in question, such as rolling a 1, which can occur in one way. The probability is then found by dividing the event by all possible events, which in this case works out to 1/6. Realize the cold calculating logic here. There is no such thing as a lucky number, no divine intervention. The probability of rolling any number is exactly 1/6. Now the same logic applies when we roll multiple dice. Imagine he needed to know the probability of rolling a pair. First, he counts the size of the sample space. With 2 dice rolls, there are 36 possible outcomes. 6 times 6. Then he counts the number of ways this event can occur. There are 6 different pairs. So 6 divided by 36 is the probability of rolling a pair, also 1/6. This simple yet powerful idea allowed Cardano to bet according to the true probability, while his opponents placed their bets based on hunches and lucky numbers. Remember, this works with multiple rolls. Imagine we needed to know the exact probability of rolling 3 ones. Simple. First, we figure out the size of the sample space. For 3 dice, this is 6 times 6 times 6, or 216. And there is only one way to roll 3 ones, so the probability is 1 divided by 216. This was the trick. It was not based on magic, but mathematics. Remember, to calculate the probability of a random event, such as a dice roll, you divide the number of ways that event can occur by all possible outcomes.
Empirical probability, also known as experimental probability. This is based on what we call the law of large numbers. The key to establishing probabilities empirically is that more observations will provide a more accurate estimate of the probability. So empirical probability is the probability of an event happening is the fraction of times similar events have happened in the past. Let's have a look at an example. Let's say we gathered this data We have a survey of 34 students at the College of Business that showed their majors. 10 people majored in accounting, 5 people in finance, and etc. From these 34 students, suppose you randomly select a student. What we want to find is what is the probability that the student is a management major. So management majors, we have 6 of them out of the 34 students. So this student, the probability that your random student is majoring in management is 6 out of 34, or 17.6%. Now, how is this empirical? Well, what if we were able to gather more data and we were able to, say, gather 100 students' information? What would happen in that case is this would change, this array would change, and therefore we may get additional information that might allow us to more accurately predict what percentage of students are management majors versus just selecting these 34. We have to ask several questions about this survey, namely, how was the survey done? Did you have a random selection of students in order to do this survey? Did you ask one specific class what their majors were, etc.? All these questions are important. But in terms of empirical probability, the more data that we gather, the more accurately we can predict the actual true probabilities. One other type of probability that we don't use in this class, but sometimes we use in real life, is what's called subjective probability. In situations where there's little or no experience or information on which to base a probability, we may be able to estimate it subjectively. This basically says that it's a likelihood or probability of a particular event happening that is assigned by an individual based on whatever information is available. The rules of addition. There's 2 rules of addition that we look at in probability. The first is called the special rule. If 2 events, A and B, are mutually exclusive, meaning that they don't overlap, they can happen simultaneously, the probability of one or the other event occurring equals the sum of their probabilities. So the special rule of addition is written as probability of A or B is the probability of A plus the probability of B. The key word in the rules of addition is the word or. That's what we're measuring when we use the rules of addition. So for example, if we had a look at this diagram, we could maybe look for the probability of event A or B or C and calculate it. The general rule is if A and B are not mutually exclusive, meaning that there is some area of overlap between the 2 outcomes. So in this case, the probability of A or B is probability of A plus probability of B, and you actually have to remove the overlap. So if we have a look at this Venn diagram here, right, this shows us the number of visitors to Walt Disney World and Busch Gardens. And the center of this Venn diagram is the overlap, which basically says guests that attended both. If we were purely interested in the guests that attended Disney or Busch Gardens, that means we have to remove this overlapping section. So if 60% of people went to Disney, 50% of people went to Busch Gardens, and 30% went to both, the probability of Disney or Busch Gardens would basically be 0.6 plus 0.5 minus the 0.3, which would be equal to 0.8 or 80%. Notice if you use the special rule in this case and added Disney plus Busch Gardens, you'd get a probability greater than 1, and that should immediately alert you to something being wrong. One more example of our special rule of addition. So we have a single 6-sided dice and it's rolled. What is the probability of rolling a 2 or a 5? We know these events are mutually exclusive because when you roll a dice, you only can see one outcome at a time. So here to calculate the probability of 2 or 5, we take the probability of 2 plus the probability of 5. The probability of 2 is 1/6 plus the probability of 5 is 1/6, and the overall probability of rolling a 2 or 5 with our dice is 1/3. Another example of non-mutually exclusive or general rule. In a group of 100 students, 40 are juniors and 50 are female, and 22 are female juniors. Let's find the probability that a student picked from this group at random is either a junior or female. So remember, we have to remove the female juniors. So here's our Venn diagram of these outcomes. So remember, we're going to remove this section in order to answer our question. So we're looking for the probability of junior or female. So we take the probability of junior plus probability of female, and we remove the overlap junior-female. So in this case, we have 50 over 100 juniors, 40 over 100 females, and 22 out of 100 female juniors. And after we finish our calculation, we find that 68% of the students are female or juniors. So in this case, the joint probability, which is defined as a probability that measures the likelihood of two or more events will happen concurrently or at the same time, that's the component that we remove. Okay, so some of you guys are familiar with the deck of cards, some of you are not, and I'm going to provide this to you guys separately as well. This is a general deck of cards. Notice in our deck of cards we have 40 cards that are number cards, and we have 12 face cards. The face cards each have a value of 10, of course along with the number card with the value of 10. There's a total of 52 cards in the deck. So the reason we use the deck of cards is it actually makes some of this probability work a lot more intuitive and easier to work through. It gives us an example that we can kind of use over and over again in order to explain and understand different types of probabilities and the rules of probabilities. Okay, so let's practice. A card is drawn randomly from a deck of ordinary playing cards. You win $10 if the card is a spade or an ace. What is the probability that you will win the game? So first, spade or an ace. Now, can a card be a spade and an ace? Yes, it can. So we have to remove that probability. First, what is the probability that a card will be a spade? That's going to be the suit. There's 13 cards in each suit. So the probability a card is a spade is 13 out of 52. Plus the probability that a card is an ace is 4 out of 52 because there's 4 aces in a deck. And we have to remove the one card that is the ace of spades from the deck. So we get a total probability of 16 out of 52, which reduces to 1 over 13. So what is the probability that you will win the $10? It's going to be 1 out of 13. The rules of multiplication. In the rules of multiplication, one thing I want to emphasize is the order of the events. This will help you conceptualize and understand how we're working through the process for finding the probabilities. The special rule of multiplication. The special rule of multiplication requires event A and B to be independent. So if events are independent, that means that the occurrence of one has no effect on the occurrence of the future event. So an example of two independent events would be rolling a dice, flipping a coin, etc. The probability of getting any number face on the die in no way influences the probability of getting a head or tail on a coin. The rule is written as the probability of A and B. So the key word in all our rules of multiplication is the word and, right? Because we're calculating a joint probability. Is going to be found by doing probability of A times probability of B. So as I mentioned earlier, we're really looking at the ordering of the events. In this case, we're saying event A happens first, and then event B happens second. Let's look at an example. A card is chosen at random from a deck of 52 cards. It is then replaced. So we take a card, then we replace it back in the deck, and then choose a second card. What is the probability of choosing a jack and then an 8? First, how many jacks are in the deck? The number of jacks in a deck is going to be 4 out of 52. If we take the card and replace it back in the deck, the probability that the next card we choose is an 8. There's again 4 8s in the deck out of 52. So what is the probability of choosing that specific ordering of events? Why, it's going to be 16 out of 704, which is 1 out of 169, which is approximately 0.59%. Very unlikely. General rule of multiplication. So the general rule is the conditional probability is required to compute the joint probability of the two events. The general rule can be written and read as such. The probability of A and B is equal to the probability of A, so event 1 taking place, times the probability of event B given that event A has occurred. This line here between B and A, that's read as the word given. What this is saying is we're saying, okay, what is the probability of this event B now that event A has already occurred? So let's look at this example. We're going to look at an example of drawing two kings from a deck of cards. So event A is drawing a king first, and event B is drawing another king second. For the first card, the chance of drawing the king is 4 out of 52. So here's our first king. Now that we've drawn that card out of the deck, and we're going to keep it, we're not going to replace it and put it back in the deck, which means now we've changed the probability of every single event to come. So after we remove the king from the deck, the second card is now less likely to be a king because there's now only 3 kings left out of a total of 51 cards. So the probability of the second card being a king is 3 out of 51. What is the probability of these two events? Event 1 followed by event 2, that would be 4 out of 52 times 3 out of 51, which is equal to about 0.45%. Now notice here we didn't specify a suit. This is a king of any suit. This is coincidence that we have a heart and a spade. Probability of blackjack. What does blackjack require? Blackjack requires one card of value 10 and an ace. First, how many cards in the deck have a value of 10? There are in fact 16 cards, the 12 face cards and the 4 cards with the value of 10. Second, how many aces in the deck? Well, there's 4 aces in the deck. So what is the probability of getting blackjack on the first 2 cards drawn from the deck? So this is like taking a fresh deck of cards, not like a regular blackjack game. So to find that, we take the probability of an ace times the probability of a value 10 card given that an ace was selected. So we have 4 out of 52, which is the probability of an ace, times 16 out of 51, which is a probability of a value 10 card, given that an ace is selected. That's why we have 51 in the denominator. And the answer is the probability of receiving blackjack on the first 2 cards drawn from a deck is 2.4%. This is just a figure basically looking at all the rules of computing probabilities, the rules of addition, multiplication, and their different equations for you guys to have for your notes. That's the end of Lecture 5, Part 1. Please move on to Part 2.